Today we're going to be looking at various types of problems that you will need to be able to solve in order to do things with molarity. So a couple of important bits of information to know about all of this. Molarity is equal to the moles per liter, right? And we know that M1V1 equals M2V2 whenever we get to those problems. And then don't forget that there are 1,000 milliliters in a liter. So if I have, 50 liters, then I can multiply that by 1,000 milliliters per liter and get 50,000 milliliters. Or if I have 50 milliliters, then it would be times 1 liter per 1,000 milliliters to be 0.05 liters, like so. So basically you're moving the decimal point 3 places if you need to go from small to big. So you need to go from milliliters to liters, 1, 2, 3, 0.05 in the liters, that's there. Or if you were in 50 liters, right, and you wanted to go to milliliters, then you would move the decimal point 3 places to get to that. So it would be 1, it would be 1, 2, 3. So there's your 50,000. So if you're talking milli, you're talking about moving the decimal point 3 places. So 1,000 milliliters equals a liter. So those are the 3 equations that we're going to need for the vast majority of all of this. So first of all, this just says what is the molarity if I've got that many moles in that many milliliters. So it wants the molarity, so it wants that. It gave me the moles, so that's 0.25 moles. And then all I have to do is convert that into liters. Well, if I've got 500 milliliters here, well, that's going to be 0.5 liters because, again, I'm going to go 1, 2, 3, move the decimal place 3 places. So I have half a liter that's there. So I have 0.25 moles in half a liter. So I should end up with a molarity of 0.5 moles per liter. So this is the same thing except backwards. They have given you grams and they want to know a number of milliliters that is here. So remember, if they have given you grams, they have also given you moles. So magnesium is 24.3, sulfur is 32.1, and oxygen is 16 4 times. Add all of that up, and I'm getting about 120.4 grams per mole for this guy here. So I've got my grams, so that's going to be 0.50 grams at 1 mole per 120.4 grams. So that turns out to be about 0.00415 moles of my magnesium sulfate. Now I'm good to go. I have my molarity is equal to the moles per the liter, right? And I want milliliters, so really I want liters. I want that guy there. So my molarity is my 2.4 molarity. My moles comes from up here. That's 00415 moles, and that's over X liters. So solidify that, and you end up with should be 0.00173 liters, but again they wanted milliliters, so no big deal. Move the decimal place 3 places, so it's about 1.7. So it should be about 1.73 milliliters should be your answer, assuming I've done my math right. For these problems, you have to decide, are you looking at a unicycle, a bicycle, a tricycle, or something else? Now, what do I mean by that? Well, let's come way down here for a second, and let's think about a unicycle. A unicycle is made of 2 parts, essentially. A unicycle is made of the seat, and a unicycle is made of the tire. Now, if I operate a unicycle theft chop shop ring, where I'm going around and I'm taking all the unicycles I could find and I'm breaking them into their component pieces, then what I'm going to do is, if I break this guy up, for every 1 unicycle, I get 1 tire and 1 seat. So every 1 unicycle gives me 1 piece of seat and 1 piece of tire. That would be similar to something like sodium chloride, Na and Cl. If I have something like 5 molarity of NaCl, then when NaCl breaks up, it's going to break up into the Cl part, which is your tire, and the Na part, which is your seat, but it's going to be 5 molarity for my sodium ion that's up here, because again, when it breaks up, it breaks into an ion. And it's also going to be 5 molarity for my chloride ion down here, in the same way that it was for the unicycle. So my unicycle breaks up into as many pieces as you have for each of the component parts. So if it's a unicycle, it's very simple. And this one here, letter A, is a unicycle. How do I know? Because it's made of 2 parts, the lithium part and the nitrate part. So when this guy breaks up, he breaks into a lithium with a +1 and a nitrate with a -1. So if it's 0.2 molarity, that means it's going to be 0.2 molarity for the lithium, and it's also going to be 0.2 molarity for the nitrate. And we usually represent those with brackets around the substance. And the brackets mean molarity. All right, well, let's say our nefarious chop shop has upgraded from unicycles to something far more lucrative like tricycles. Well, if you have a tricycle and you take this guy apart, well, then you're going to end up with, for every 1 tricycle, you're going to end up with 1 part of the frame and 3 parts of the tires over here. So for every 1 tricycle, you get 1 frame and you get 3 tires, right? Because you break it apart and you get all those different tires out of it. So logically speaking, then, if I were to have whatever 5 tricycles, then I would end up with 5 frames, and I would end up with 15 tires over here, because each tricycle would give me 1 frame and 3 tires. So why do I bring tricycles up? Because that's our next one here. Our next one is aluminum nitrate. So let's check this guy out. I've got aluminum and nitrate. When this guy breaks up, he breaks into the aluminum with the +3 ion, and he breaks into 3 nitrate ions, like so. So for every 1 aluminum nitrate, every one of those, I get 1 of those and 3 of those. So when this guy busts into his component pieces, for every 1 of these, I'm going to have 1 aluminum. So if I have 0.3 of this, I'll have 0.3 for my aluminum. So my aluminum is going to be 0.3 molarity, because the aluminum is my frame. There's only 1 of them there. But I've got 3 tires. I've got these 3 tires here, 1, 2, 3. So if this guy here breaks up into its pieces, it's going to be 3 times that number in order to account for the different nitrates. So the nitrates are actually going to be 0.9 molarity for the nitrate, because every 1 aluminum nitrate gives you 3 nitrates. Well, our chop shop went straight from unicycles to tricycles, so clearly there is a market for bicycles as well, and hopefully by this point you can figure out what the trend is. For every 1 bicycle that you chop up, you are going to get 2 tires out of it. So you're going to move that guy and you're going to move that guy. So for every 1 bicycle, you get 1 frame and you get 2 tires. So if I had 100 bicycles, then I would have 100 frames and I would have 200 tires over here. So again, if I have 100, then I'm going to end up with 100 frames, but I'm going to end up with 200 tires over here. So in chemistry, it's no different. It's just that it kind of looks scary. So here is one of ammonium carbonate here. Well, ammonium carbonate is a bicycle. It's a really weird looking bicycle, but it's still a bicycle. This is going to be NH4 plus 1, and it's going to be that twice. And then this is going to be CO3 with a -2. So for every 1 ammonium carbonate, you get 1 carbonate and you get 2 ammoniums out of it. H4 like so. So if you have a 0.75 molar solution here for this guy, then you are going to end up with the same number of carbonates, because the carbonate is only 1 in there. So your carbonate is going to be 0.75 molar of your carbonate in brackets. But your ammonium is going to be twice that, because there's 2 of them there. So your ammonium is going to be 1.5 molarity of your ammonium, like so. Letter D here, I have absolutely no idea what real-world complement this would be, but hopefully by this point you've figured out how this process works here. So if you've got aluminum and you've got sulfate, assuming this thing breaks up entirely, there are 2 aluminums that's there, so that's going to be 2 aluminum plus 3. And there are 3 sulfates that are there, so that's going to be 3 SO4 minus 2s. So for every 1 of these guys that breaks up, you get 2 of those guys, but you get 3 of those guys. So if it's 0.25 molar in the aluminum sulfate that's here, then you're going to proportionally do the same thing that we did to the bicycles and tricycles and unicycles above. Your aluminum is going to be twice that, because again there's 2 of them there, so it's going to be 0.50 molarity for the aluminum ions, and the sulfate is going to be 3 times that, so that's going to be 0.75 molarities of the sulfate. Number 5 is a simple dilution problem. Here's our first M1V1 equals M2V2. How do you know that? Because they gave you a volume, they gave you a molarity, they gave you a new volume that it has been diluted to, and they want to know what the new molarity is here. That's X. So this is a simple plug and chug. Remember on these guys, they don't have to be in liters. They can be in any unit provided the unit is consistent. So this guy is milliliters and this guy is milliliters, you're good to go. If this guy was milliliters and this guy was liters, you'd have to convert one to the other. Wouldn't matter which one that you did in this problem as long as they are both the same. So regardless, what we've got here is we've got a 12 molarity solution at 30 milliliters. That is going to be diluted to some new X molarity, I don't know what it is, times 300 milliliters. So we divide by 300 on both sides and go to town. And your X molarity should end up being 1.2 molarity. Number 6 is no different than number 5. We're just looking for a different variable. It's another dilution problem. So it tells us that we have 50 milliliters of 0.75 molar solution, so that's V1 and M1, and we want a new molarity, M2, to be 0.25, so it wants to know what the new volume is. That's what our X is. So this is 0.75 molarity times 50 milliliters is equal to 0.25 molarity times X. So you plug those things into your calculator, and you end up with an answer of 150 milliliters as your V2 that's there. Number 7 is kind of an annoying problem because you really have to be able to combine all of the ideas that we have done before, but if we systematically go through it and take a look at it, it should be fine. So what we're doing is we're combining a solution of calcium nitrate with a solution of aluminum nitrate, and it wants to know the final concentration of the nitrate. So let's look at each of them in turn and kind of forget about the others. So first of all, let's look at what we got here with our calcium nitrate solution. So we've got a beaker and it's got 200 milliliters of 0.45 molarity of the calcium nitrate. Now, we're only concerned about the nitrate. So what I'm going to do, I'm going to use my bicycle tricycle kind of logic and realize that if it's 0.45 molarity of the calcium nitrate and I really only care about the nitrate, then I'm going to realize that this is a bicycle because there's 2 nitrates for every 1 calcium nitrate that's there. So really it's 0.90 molarity for the nitrate ion because it's going to be twice of the 0.45. So I'm going to get rid of this. I really don't care about this. So what I now have is I now have 200 milliliters of 0.90 molarity of my nitrate from my first beaker. Now, let's go ahead and see what's going to happen to that individual solution, right? Let's forget about the other one for a second, and let's look at just this one here, because apparently what we're going to do is we're going to take 200 milliliters of it and we're going to combine it with 100 milliliters of it. So this has now just become an M1V1, M2V2 problem. So this is going to be from 200 and we're going to combine it with the other one, so it's going to go up to 300 milliliters because again we're going to combine it with the other solution. Erase my bicycles here. So again, what we're going to do here is we're going to take a 100 milliliter solution of the 1.2 molarity of the aluminum nitrate, and we're going to combine the two of these guys together so that it's this brand new beaker here of 300 milliliters, right? That's what we're ultimately going to do. But back to this one here, we're going to take 200 milliliters of 0.9 and increase it to 300 milliliters. So what is our new concentration from beaker 1? Well, this is just going to be M1V1 equals M2V2. So this is going to be 0.90 molarity times 200 is equal to X times 300 milliliters. And our new X, when we do that, is going to be 0.6 molarity for the nitrate. Now, if that's all there was, then that would be your answer, right? Your answer would be 0.60 molarity of the nitrate. But turns out that this other solution also has nitrate in it. So that's going to be combined with this other nitrate that's up here to make a new concentration. So let's now do the second problem, which is this guy here. So once again, this is a bicycle-tricycle situation. And so what we have here is we have 1 aluminum and 3 nitrates with a 1.2 molarity, and it's a tricycle situation because of the 3 that's there. So really what we have here is we have 3.6 molarity of the nitrate because it's 1.2 tricycles, but we're interested in the tires, so it's really 3.6. So I'm going to get rid of this now because I really don't care about the aluminum. The problem doesn't say anything about that. So I have 100 milliliters of 3.6 molarity nitrate, and what am I doing? Well, I'm combining it with this other 200 milliliters up here to make a new total volume of 300 milliliters. So this becomes its own M1V1 equals M2V2 problem. So this is now going to be 300 milliliters of I don't know what the concentration is. Okay, well I can figure that out. So what I've got here is I've got 3.6 molarity times 100 milliliters is going to be equal to X molarity times the 300 milliliters. And I'm going to go ahead and solve for that. So 3.6 times 100 divided by 300 is going to be 1.2 molarity of the nitrate here. So, final answer here, what we have is two things going on. From this top equation up here, we have that the nitrate is going to be 0.60 molarity. But from the bottom equation down here, we have that the nitrate is going to be 1.2 molarity. So, if part of it is 0.6 and the other part of it is 1.2, all you do is add them up and combine them, and your final concentration is 1.8 molarity for the nitrate ion. Now that's pretty complicated. I don't know that you're going to get something like that, but what it really comes down to is just doing two individual problems. One problem for the first beaker, one problem for the second beaker, and then you combine them.